bilinear transformation which mod z less than equal to 1 maps into mod w less than equal to 1 can be put in form w equal to e the power iota lambda az plus b divided by b bar z plus a bar, where this lambda is real. Right, we have to get this bilinear transformation. And then secondly, if z equal to 1 is the only invariant point, then this bilinear transformation can be put into form 1 over w minus 1 equal to 1 over z minus 1 plus 1 over k, where k is 1 plus a bar divided by b. Right. So let's move on to the solution. Let's write our original transformation, that is w equal to az plus b divided by cz plus d, with a very important condition that AD minus BC is non-zero. So let this be the required transformation, and we require mod W equal to 1 when mod Z is equal to 1, right? That is, we have to just put the value of the transformation over here. So this becomes mod of AZ plus B divided by CZ plus D is equal to 1. That is, mod of AZ plus B equal to mod of CZ plus D. And let's square both the sides so that I can write this further as, because I know that mod of Z square is equal to Z into its conjugate, right? So writing this as AZ plus B into its conjugate, that is A bar Z bar plus B bar, that is equal to CZ plus D into its conjugate, C bar Z bar plus D bar. Fine. Okay. So let's multiply these two, and after multiplying or simplifying this, we get this equation in terms of z bar, z bar, right? So the coefficient of z bar is, on simplification, the product of a bar minus product of c bar. This is a coefficient for z bar, and then writing the coefficient for z, that is a bar minus c d bar, and the coefficient of z bar is ba bar minus dc bar. This is the coefficient for z, and this is equal to, on the right hand side, dd bar minus bb bar. Please mark this as 1. Now this 1 will be in the form zz bar equal to 1 if the coefficients of z and z bar is 0. So let's put the coefficients of z and z bar to be equal to 0. We get ab bar minus cd bar equal to 0 and ba bar minus dc bar equal to 0, right? And when putting these two equal to 0, we get the equation 1 as, because this is 0 and this is 0, we get product of a bar minus cc bar into z bar is equal to dd bar minus bb bar. So 1 becomes a bar minus cc bar equal to dd bar minus bb bar, right? Please mark this set of equations as 2 and mark this as 3. Now for this set of equations, let's suppose that if a is non-zero, then the set of second equations, this will gives us the value for b bar we can get from the first equation as, because a is non-zero, so we can write the value for b bar as cd bar divided by a. A is non-zero, and from the second equation we get the value of b as dc bar divided by a bar, right? For this transformation I need the value of c and d, so that I can put the values of c and d over here, right? Now let's put these two values of b and b bar in this third equation, right? So this left hand side, that is the product of a bar minus cc bar, is equal to dd bar minus the product of these two. So this is equal to d bar minus the product of b and b bar, that is c bar into d bar divided by a bar. And then let's take the LCM, and taking the denominator a bar to the left hand side, and this is equal to a bar into d bar minus c bar into d bar. So this is equal to taking d bar common. So this is a bar minus c bar into d bar. That implies a bar minus c bar, this factor multiplied with a bar minus d bar. So this implies taking this factor common, we get a bar minus c bar into a bar minus d bar equal to 0. And this a bar is nothing but mod a square, and this c bar is nothing but mod c square, right? And this d bar is mod d square. What happens if mod a is equal to mod c? So if mod a is equal to mod c, we write c as a into e the power iota lambda, where this lambda is real. And from here I can get the value of c bar as a bar into e the power negative iota lambda. And then putting this value of c bar in the equation 2, that is the set of equations in second equation for the set of equation 2, I'm putting the value of c bar over here, b a bar minus d c bar, where c bar is this, a bar into e the power negative iota lambda equal to 0. This implies this a bar cancelled out, and then we can get the value of d from here, that is d is equal to b into e the power iota lambda. Yes, this is the value of d. So now I'm having the value of d, and also I'm having the value of c, right, from here. So we just need to put these two values in our original transformation. So this transformation reduces to, for mod a equal to mod c, for this case mod a equal to mod c, the transformation reduces to w equal to az plus b divided by cz plus d. What is the value of c? It is a e the power iota lambda, and the value of d is b e the power iota lambda. So this becomes az plus b divided by, taking e the power iota lambda common from the denominator, so this becomes az plus b, which cancelled out, and this is 1 over e the power iota lambda, or it can also be written as e the power negative iota lambda. Yes, so this implies the transformation reduces to w equal to e the power minus iota lambda, which is not a bilinear transformation. Yes, so this is not a bilinear transformation. Now if mod a equal to mod c, we don't get the bilinear transformation. Yes, okay, so the other case, this is what, this is nothing but mod a square. What happens if mod a is equal to mod d? The other case, if mod a is equal to mod d, this implies I can also write this as mod of a bar is equal to mod d. Yes, I can write like this. Okay, then d e the power iota lambda, where lambda is real, or I can also write d from here as a bar e the power negative iota lambda, where lambda is real. So I got the value of d, and now required to get the value of c. From the value of d, I can get the value of d bar as a into e the power iota lambda. Yes, and substituting this value of d bar in the first equations of the set of second equation, that is here. And on putting the value of d bar in this first equation, I can get the value of c. Yes, okay. So substituting d bar, we get AB bar minus CD bar. Instead of D bar, I'm substituting its value, that is A e the power iota lambda equal to 0. So this A cancelled out, and from here I can get the value of C as, this B bar is equal to C e the power iota lambda, and from here C is equal to B bar into e the power minus iota lambda. And now I get the value of C also. So I'm having the value of C, also I'm having the value of D for mod A equal to mod D. So the transformation reduces to, this is my original transformation, and putting the value of C and D over here, we get, this is AZ plus B divided by C is B bar e the power minus iota lambda plus D is A bar into e the power minus iota lambda. A bar into e the power minus iota lambda. So this is equal to, taking e the power minus iota lambda common, or I can also write this as in the numerator, that is e the power iota lambda into AZ plus B divided by B bar plus A bar. Hence, we get the required bilinear transformation where AA bar minus BB bar is non-zero. That is, mod of A is not equal to mod of B. Fine? Okay. Please mark this transformation as 4. Now to examine the correspondence between the interior and the exteriors, for that let's consider W bar minus 1. Right? So what is W? It is e the power iota lambda into AZ plus B divided by B bar Z plus A bar into its conjugate, that is e the power negative iota lambda into A bar Z bar plus B bar divided by BZ bar plus A minus 1. If you multiply these two, you get this to be as 1 into, multiplying the numerators, we get AA bar into ZZ bar plus AZB bar plus BA bar Z bar plus BB bar minus the multiplication of the denominators, that is BB bar into ZZ bar minus B bar ZA minus A bar BZ bar minus A into A bar, right? And divided by the denominator, that is B into Z bar plus A into B bar Z plus A bar. So on simplifying the numerator, you get this to be as ZZ bar minus 1 into AA bar minus BB bar divided by, now this thing is just the conjugate of this factor, so this can be written as mod of A plus B into Z bar whole square, right? And now the conclusions. When mod Z is strictly less than 1, that is, when mod Z is strictly less than 1, which means if you square both the sides, you get this to be as ZZ bar less than 1, strictly less than 1. That is ZZ bar minus 1 less than 0, which is this factor, the first factor of the numerator. So which means if ZZ bar is less than 1, then we have mod of W strictly less than 1 or mod W strictly greater than 1, according to as mod A is greater than mod B or mod A is less than mod B. For mod W less than 1, we have mod A greater than mod B, right? And for mod W greater than 1, we have mod A strictly less than mod B, accordingly, right? But we need mod W less than 1, the interior of the circle. So for that, we consider mod A greater than mod B, considering the second factor also with this. It follows that the bilinear transformation maps mod Z less than equal to 1 conformally into mod W less than equal to 1 only when mod of A is strictly greater than mod of B. That is this case. Right? Okay. Now to get the invariant points of the transformation. Now what is the invariant point? That is to get the fixed point. And how do we get the fixed point? Just replacing w with z in the transformation. That is z equal to e the power iota lambda az plus b divided by b bar z plus a bar. On simplification, let's get the quadratic equation in z as, that is b bar z square plus a bar minus a e the power iota lambda z bar minus b e the power iota lambda equal to 0. Now it is given to us that if z equal to 1 is the only invariant point, then invariant point, because I'm having b bar as the coefficient of z square, so for z equal to 1 as the only invariant point, I can write the quadratic equation of z as b bar into z minus 1 whole square equal to 0. And I can also equate this equation with this. So we get this. And now equating the coefficient of z from both the sides, we get a bar minus a e the power iota lambda equal to minus 2b bar, and also equating the constants, we get minus b e the power iota lambda equal to b bar. Please mark this set of equations as 5. Now I can write this first equation as a bar minus a e the power iota lambda plus b bar equal to minus of b bar, and putting the value of b bar over the right hand side only. So I get a bar plus b bar equal to minus b bar plus a e the power iota lambda, and also putting the value of b bar over here. So we get a bar minus b e the power iota lambda equal to minus b bar plus a e the power iota lambda, or a bar minus b e the power iota lambda is equal to a e the power iota lambda minus b bar. Please mark this as equation 6. Now to get this format, let's find the value of w minus 1 first. So w is e the power iota lambda into az plus b divided by b bar into z plus a bar minus 1. So this is equal to a into e the power iota lambda into z plus b into e the power iota lambda minus b bar z minus a bar divided by b bar z plus a bar. Now taking its reciprocal, we get this. Taking z common from the denominator, we get a e the power iota lambda minus b bar into z plus b e the power iota lambda minus a bar. Taking the coefficient of z outside, and we get this. Fine. From equation 6, this right hand side is equal to negative of b e the power iota lambda minus a bar. Yes, so this complete becomes negative 1, and we get b bar z plus a bar divided by a e the power iota lambda minus b bar into z minus 1. Now working in the numerator, what you have to do is you just need to add and subtract b bar divided by a e the power iota lambda minus b bar into z minus 1. We need the factor z minus 1 in the numerator. So just taking b bar common, we get b bar into z minus 1 plus a bar plus b bar divided by the denominator. And now just separating the terms, we get the first term becomes b bar divided by a e the power iota lambda minus b bar, and second term becomes a bar plus b bar divided by a e the power iota lambda minus b bar into z minus 1. Right? Okay. If you notice this equation, I'm having the sum of a bar plus b bar as a e the power iota lambda minus b bar. So just using this now over here, a into e the power iota lambda minus b bar. So this also cancelled out, and writing this as a bar plus b bar, right? Okay, so this is equal to, taking b bar common from the numerator and the denominator, that becomes a bar divided by b bar plus 1 plus 1 over z minus 1. And the left hand side is 1 divided by w minus 1. Yes? Okay. Let's write this factor as k. So we get 1 divided by w minus 1 equal to 1 over z minus 1 plus 1 over k, where this k is equal to 1 plus a bar divided by b bar. Yes? Hence proved. So the required bilinear transformation can also be put in the form this. Fine? Okay, thank you.